actually have too much to go through today, because like the RTES topic itself is very much theoretical, at least in this course. So a basic understanding of sort of the principles of mutexes and semaphores and whatnot is very good, but you can't do too much sort of question problem solving on it. One thing I would probably want to go through quickly that I find when I teach real-time sort of operating system principles that students sort of struggle with or get a bit caught up on, I did as well when I was studying still, is like what mutexes do on top of a normal semaphore. And so how they're actually better when they implement priority inheritance to solve priority inversion. So before I go and do the questions on scheduling, I'm just going to do a quick explanation, sort of handwritten notes on what priority inheritance is, so that when people watch this, probably in the New Year's, they'll be able to have all their questions asked. Now, let's do it here. So if anyone has any questions, for those that are actually in the call, feel free to speak up. The chat I won't really have open that much because I am only on one little laptop screen. So maybe just make a noise or something so I know the question's being asked. But essentially what priority inversion is it's a problem that we get when, I want to go before, I said before, oh well. So the problem that we have is that when you use a semaphore, and so a semaphore is what lots of people would refer to as a lock, and it's used to protect resources. But when we're doing like a multi-threaded program, if they both want to access the same sort of variable, so some sort of memory region, how do we stop them both concurrently trying to access this data? Because if you think about it in terms of sort of like how the CPU is doing it, one task is maybe reading the memory location, and then it will get sort of interrupted, and the other one goes to read it, and then it gets interrupted, and the first task goes back to write back. But in the meantime, other stuff's happened, and you can sort of get corrupt values in memory. And so to stop this happening, you need to somehow have a lock. And what it does is it sort of means that the variable is privileged, and that only one task can actually have control of this variable, or whatever it is, essentially just some region of memory. And so it can take the lock, do what it wants to do, and give the lock back to say, I'm done accessing this memory block, and then another task can come in. But there's a common problem that we have, which I'll explain with a nice little pretty picture in a second, which is called priority inversion. And what it means is that a task of medium priority on a system can actually end up superseding a high priority task through the fact that semaphores don't have priority inheritance.
We can't see your screen.
Yep.
We can't see your screen.
Yes, I'll share it now. Good thing I haven't started yet. Okay, so a semaphore, it's just like a real basic sort of example, is that we can have three tasks, and we'll say here that like the highest priority. So we'll just go, where's my pen? We have three tasks, 3, 2, and 1. So this is task number and priority. Now let's just say that we have our low priority task executing, and it wants to obtain a resource. When it does that, it takes a little flag, and it can continue executing. Now, if we're on a preemptive system, so preemptive, and this problem is unique to preemptive systems, but preemptive systems is extremely common today. So a preemptive system means that one task can be interrupted by another task when the other task has a high priority. So in this case, if task 3 at this moment in time wants to start executing, it can preempt task 1 because it has a higher priority. And so this is what this blue is, it's a preemption. And so then task 3 can start executing. But now let's say that task 3 wants the same resource that task 1 controls, right? So it's going to attempt to take the resource. But it can't, because the resource, like this lock, is still held by task 1 because it didn't release it before it was preempted. And so what happens then when we're dealing with usually these calls to obtain a lock involve blocking. So you can either specify, okay, block or don't block. And generally with a lot of critical things, like the task won't have much else to do unless it can obtain the resource. So they generally just block forever until they can obtain the lock. And so in this case, where did I go? Uh-oh. So what would happen here is that the task 3 can't get the resource, and so it's going to surrender the CPU back because it's essentially going to go into a blocked state. So we'll get here, task 3 blocks because it can't get the resource. And so we're going to then get another sort of CPU surrender, and task 1 can continue executing. So now we're at this right now is where the problem can happen. So task 1 is executing, but we have this medium priority task, task 2. On a preemptive system, it is allowed to preempt task 1 because it has a higher priority. And so it can do that. And that's exactly what's going to happen with this priority inheritance problem. So right now, task 2 is going to preempt. Why does it do that? And execute. Now this is valid because nothing wrong has happened. It's got a high priority. We're on a preemptive system, and so it's preempted a low priority task. But the overall problem is that our system is currently running a medium priority task, task 2, when it should be focusing on releasing the resource to get task 3 to run, because it's the highest priority task, and we should be focusing on getting this task to run. So this here is the problem of priority inversion. Because given this, we're essentially saying task 2 is more important than task 3. And this is bad. How we can fix this is instead of using a semaphore, we use a mutex. And so a mutex is by all means used the same way as a semaphore is in classical operating systems. It's used as a lock. It's used to lock resources to make sure that we don't have simultaneous accessing, but it is essentially a semaphore with some extra sort of overhead and features, and namely it implements priority inheritance. And so we draw the same little picture again. We'll have the exact same sort of sequence of events. We'll obtain the semaphore here, and then we'll jump up to here. He's going to try and get it and surrender the CPU again. So this is all the same. Now we get to this point where task 2 wants to preempt. But the thing that stops it from being able to preempt is that at the moment that this resource is tried to be obtained. So right here, we raise task 1 priority temporarily to that of task 3. So we can think about it right now is that for this execution chunk here, this is priority 3. It's temporarily raised. Because by doing this, we're sort of saying, okay, set the focus on where this resource is being obtained and like get it to release. And so at this point in time here, when task 2 wants to then preempt again, it can't. And so we're just going to continue executing, and it will release its resource. And at that point in time, task 1 can take the resource and continue executing. Or task 3, sorry, I should say. And so this here is the solution. This is priority inheritance. Oops. And this is good. And so this would be a mutex. This would be a semaphore. So is this clear to those few people that I have listening? Okay, so if there's no questions on that, then I'm just going to get sort of cracking into the scheduling sort of exercises. There is one more sort of exercise I could go through quickly that I didn't really find a good question write up of, and I didn't really have enough time to get it prepared, so I thought I would just do it on the fly. And that's sort of just like manually thinking about the difference between preemption and like a preemptive systems and non-preemptive systems in terms of like a visual scheduling sort of diagram that we would draw up. And so this can be really easily visualized. I mean, we might even ask this in the question in the exam to sort of just draw out the scheduling sort of timeline for a set of tasks given their priorities and their periods. So let's say that we have 3 tasks. Again, we have tasks 1, 2, and 3. And we want to say, for instance, then here we'll use rate monotonic priorities. So this will say RMS priorities. And what this means is the shorter the period of a task, the higher its priority it is, right? So shortest task period equals highest priority. And this scheduling policy, as you can imagine, is very much aimed at just getting the things that need the deadlines are coming up soonest, get them done quickest, right? And in a lot of cases, using RMS is the optimal scheduling policy because it sort of deals with the close at hand problems. So if we use RMS, or let's first actually get a couple of more like stats for each one. So we're going to need a period, and we're also going to need an execution time. Right? And so then we can also calculate the priority here. So I'll take these. So let's just say like 6, 8, 9, 2, 3. We'll just make a couple the same length, 2, 3, 2. And so if we think about the priorities here, this is going to mean that we have, the period here is the shortest. So it's going to get the highest priority. So this is our second priority task, and this will be our this should be the other way around. Priority 3, our highest priority task, our medium priority task, and this will be our lowest priority task. Okay, and so then we can think about scheduling this set of tasks onto 2 separate systems. So we could have a non-preemptive system, and maybe this example sort of actually also highlight that preemptive systems, while you might think, oh, that sounds awesome, like that's got to be better most of the time, but sometimes preemptive systems are actually inferior, or they don't schedule, they can't get sets of tasks scheduled as well as non-preemptive systems. So what common denominator are we going to need here? With the periods of 9, we'll probably go about 27, I would say. Should do us. 25, 10, 15, 20, 25. So these are ticks, and so the tick is when the scheduler is invoked. So this needs to be, oh man. So now we're going to say this is I'm pretty sure this is called the critical moment. And so the whole idea is that if you want to determine if a set of tasks is schedulable, you start them all at the same exact moment in time. And if they are schedulable at that moment, then they're always going to be schedulable, because that's essentially the worst case, right? If you just start all your tasks at once, you can imagine you have the highest sort of immediate workload. And if your system can handle this, then you sort of set with whatever combinations or starting offsets you can think of. So now let's think about our task. We have task 1 is our highest priority task, and it's going to execute first. And so it's going to execute for 2 ticks because we have an execution time of 2. And so we're in a non-preemptive system here. And so we don't have to worry about getting interrupted or anything. But then if we look, for instance, at the period, we can sort of write on our diagram where this task's deadlines are going to fall, like when this task needs to be completed by, such that we don't violate its deadlines. So it's going to have to execute by the 6th tick, so here, the 12th tick here, the 18th tick here, 24th tick here. Yep. And we'll just quickly then do this for the other 2 tasks, a period of 8. So we're going to have 8 here, 16 here, and it's also going to run on the 24th tick here. Then the green, 9, 18, and we'll go on to 27. So now we've drawn in our first sort of task 1's first execution block, and it's going to finish up here. And so we're now at the point here, 2nd tick, where we need to choose the next task to run. So obviously task 2 and 3 still need to be run. They're still waiting. So task 2 is going to run because it's our medium priority task. And so we're going to then schedule task 2, and it's got an execution time of 3 ticks. So it'll run here for 3 ticks. So now task 1 hasn't reset yet. It hasn't had its period. So it's actually still blocked, and it's not ready to go onto the CPU. So the scheduler will ignore it because it doesn't have the ready state yet. It will then, once this period has been met, then the task will become ready again, and the scheduler will start putting it back onto the CPU if it can. So at this point in time, only task 3 is left to run. And so we have 2 ticks here. So it's going to execute here. Now, at this moment in time, tasks 2 and 3 haven't had their first period yet. And so they're still going to be finish running suspended in a block state. They're not going to be ready. But since we've had the 6th tick happen, task 1 is now ready. And so it can be scheduled onto the CPU again. And so that's exactly what's going to happen. At this point in time, we're going to have task 1 run again. Then we have sort of a bit of a sort of repeat. Task 2 is now ready again. And so it's going to run for 2 ticks or 3 ticks. And so now task 2 and task 1 are blocked. We only have task 3 left to run. And so it's going to run for 2 ticks here. Actually, wait, sorry, my bad. No, it's not. As we can imagine, so now we're at the 12th tick. And so task 1's period is now come around again. So it's now ready. And so we have task 3 and task 1 that are both ready. Task 1 has the highest priority. And so what this means is that we're going to have task 1 run again for 2 ticks. And now we can run task 3 again. Then we'll go task 2 will be ready, and it will run task 1. Then we'll have task 3. Yep. Task 1, etc., etc. So that's how we would manually draw out the scheduling of this system. So it's quite straightforward with non-preemptive, because you literally just think at each moment in time, you draw in the block for the entire execution because the task cannot be interrupted during its execution. Then you'll sort of look, okay, what tasks are ready? What can we run? Which is the highest task? We choose the highest one, we run it, and we run it through to completion. Now things get a bit different when we want to do a non-preemptive system. I'll have to zoom out a bit here. I'm going to run out of. So now preemptive, sorry. And so what this means is that tasks can be interrupted. Meaning that at moments, for instance, like here, what would happen is that task 3 is not finished executing, but task 1 becomes ready. And since it's a high priority, it would then block task 3 and it would execute. And as you can imagine, this can have consequences in that it will push the execution of task 3, which we'll see in a minute, back so that it doesn't meet its deadline. So we actually don't need to run through this example very much, because we'll see very quickly that this right here with a preemptive system is a problem. So we'll just do the same rough time. We don't need as many ticks though. So the first thing we have our periods. So task 1 here and here, 8, 16, although I don't think we'll need the second one, and 9. Now we'll start the system the exact same way. Task 1 will run for 2 ticks. Then we've got task 2 running for 3 ticks. And now we have the, at this moment in time, task 3 is the only one that's ready. And so it's going to run. But we'll see that we have the period of task 1 coming up. And so it's going to essentially put task 1 back into a ready state. And that means that the scheduler is going to put it back onto the CPU because it's got the highest priority. And we're on a preemptive system. So it'll run for 1 of its 2 ticks of execution time. So as we can see here, it needs 2 cycles, essentially 2 ticks. So it's going to get half of it done. So we still need to execute another half before we get to its deadline. But the problem is that now task 1 wants to run. It has the highest priority. It's going to run here. So it's happy. And then we're going to reset task 2. And so it's going to want to run for 3 ticks. So essentially here. And we have this problem now that we still have half of task 3 to finish its task, and its deadline has now not been met. So with this set of tasks on a preemptive system, we can't meet the deadlines, and with a non-preemptive system, we can, right? Now, this is when you need to be sort of careful, because if we do, for instance, a very simple test to test for CPU utilization, it will show us maybe that it's schedulable. But if you actually put the tasks down on paper and look at how they would get scheduled, you would see that it actually cannot meet the deadlines. And so in the lecture, I showed a really simple, like a really simple formula, and it should make sense to everyone, is that the utilization of a system is the sum over all the tasks of the execution time over the period of the task. This is sort of just saying how much of the CPU's workload is generated from this task, given how long it takes and how often it needs to run. And so if we were to do this, we would see, for instance, that we would have 2 over 6 plus 3 over 8 plus 2 over 9. So this would be like 0.33 recurring plus about, what's that, like 3.375, 0.375 plus 7/9, about 0.22. So what that gives us, like 6.9.3. And so this is less than 1, because as you can imagine, 1 means 100% CPU utilization. And so this means that using a utilization test, this says, hey, yep, it's schedulable. But you shouldn't stop when you've done this and say, great, schedulable. Because as we could see before, if this is on a preemptive system, this is not schedulable. And so we need to do further analysis. But we can use this utilization test as an initial quick test, because I mean, it takes 2 seconds to do this, to say, okay, cool, it might be schedulable. Because if this here was greater than 1, I could guarantee and say with confidence, no, this is not schedulable. We don't need to investigate further. But if you get less than 1, then you sort of say, okay, let's go and investigate this one a little bit more. And so that's what we'll do. We'll do this with this set of questions here, this sort of set of tasks. And so the first sort of task, the first sort of question is almost, I mean, it's pointing to the same thing. If I was to read this as a student in the exam, I'd be like, okay, cool. They want me to do the utilization test, and it's going to be more than 1, right? And so let's do that. So we have these tasks here. So we have the utilization. We'll just repeat the formula is the sum over all of the tasks of the execution over the period. And so for this set of tasks here, this is going to mean that we have 2 over 4. So we have a half plus a fifth plus a 2/3 plus 4/10 plus 6/12, so another half. So this is going to give us a half plus a fifth plus a third plus 4/10 plus a half. And so what's this going to equal up to? 1. Sorry, I've got to miss. I know. So 1, it's going to be 2 point. 2.26. And so the next question is sort of saying, what's the minimum number of processes I'm going to need to schedule this, like this set of tasks? And as you can imagine, one processor, sort of generically speaking, equals 100% utilization. And this equals 1, in terms of this. So therefore, we need at least 3, because 2.26 must be less than 3, right? So that's the first question. Why can't it? Well, this here is, for instance, Y, and then this is what is the minimum number of processes? This is B. So Y is not, because it's greater than 1. And so this is greater than 1, therefore not schedulable with 1 CPU. And so this is generally like the assumption is that you have 1 CPU unless specified otherwise, right? So now we have to say, given a valid mapping, actually, I don't think we're going to do this question because it's going to take too long. We might get back to it because I want to get into the fixed point analysis, because we don't so much go into that type of analysis anymore in this course. So this is sort of where you would go with the next step. So I think, for instance, this here, this next question is a better replacement for C. So that's why we're going to sort of ignore C, because what you would normally do is you would get given your set of tasks, and then you would initially do utilization to check to say, okay, cool, my tasks are less or greater than like 1 in utilization, meaning, okay, definitely not schedulable. Okay, maybe schedulable. Let's investigate further. And if you get to the case where it's like, okay, maybe we should investigate further, then you need to do a fixed point calculation. And what this really means in simple terms is that you're going to try and calculate the worst case response time, meaning the time, worst case response time being the time your task takes to execute with regard to like interrupts from other tasks and all the delays. And you're going to continuously calculate this given your new knowledge. Like each time you calculate it, you'll get a bit more knowledge on like what the response time is, and you'll keep calculating it until you reach a steady solution. And so when you get the same solution in a couple of iterations, you've reached sort of your final solution. And no matter how many times you do the iteration or another calculation, you're going to get the same value. And this is your steady state response time. And so this is the response time that we want to find, and then check if this is less than the period for each task. So each task response time needs to be less than its deadline for our system to be schedulable. And it's really quite a simple calculation, and it uses one main formula. And that is that the response time, so R, of a task, I, so N here is this is the iteration. This is the task number. So the response time is equal to the execution time of that task plus the sum of all tasks with a high priority. So HP, this is higher priority, So all tasks, high priority of I. And what we do is we take the ceiling, meaning that we're rounding up to the next integer. So you can't, like, we don't want to have a response time of 0.2, 0.1. 0.2 would become 3, 0.1 would become 3, just like 0.7 would become 3. So what we're going to do is we're going to take the response time of the previous iteration. So this is response time of task I again, but n minus 1. And so this is where this sort of this iterative calculation comes in, because in the formula, we're actually using the response time of the previous iteration. And so you're going to keep calculating to get the new one, and it'll become fed into the next iteration, And so this is going to go over the period of the task, of the higher priority task. And this has to be less than the deadline of the task, right? And so if we do a calculation, like let's do sort of the initial calculation, usually would start with your highest priority task, because the good thing is with the highest priority task, this whole set here doesn't exist, right? There is none of it. So it's a super simple calculation, right? And if you can think back to the preemptive system, the response time of task 1 is always going to be just this execution time, because it can't get preempted. It can't get delayed by anything since it's the highest priority task. And so if we go and do this, we'll do for task 1. Then we have essentially the response time of task 1, iteration 0 is just equal to the execution time of task 1. And so this equals 2, right? And if we were to go on and do the second iteration, it would still be the same, just E1, so it equals 2, right? Therefore, response time of task 1 equals 2, and this is less than its deadline, which is 5. Therefore, task 1 is schedulable. So that one's pretty simple. Now we'll go on to task 2. And so here we actually do have a set of high priority tasks. We have task 1 to take into consideration. So what we're going to do is this sort of the first iteration, R2 equals 0. And in the first iteration, we don't have this n-1 term. So the first iteration of each one is just the execution time. So this is just going to equal the execution time of 2, which was 2 as well, right? So then we're going to go on to the next iteration. And this is where things now, we start using the complete formula. And so this is going to equal execution time of task 2 plus the sum of the higher priority task. This is task 1. So we're going to use the ceiling of response time, the previous one. So this is response time 2, iteration 0, over the period of the higher priority task. And so we're dealing with task 1 here, which has a period of 5. And then we're going to times this by the execution time of that task. So this is going to be multiplied by 2. So this is from task 1, task 1, task 1, because it's the higher priority task. It's the set. And so then we can do this calculation. This is going to be 2 plus the ceiling of 2 over 5 multiplied by 2. So this ceiling here will give us 1. This is going to be 2 plus 1 times 2 gives us 4. Now we can see that 2 and 4 are not equal. And so we need to continue doing more iterations until we reach a steady state solution. And so therefore we just go R22 equals, and we'll just go directly to numbers. So that what we do now is that this term here is now being substituted out with the previous iteration. So instead of 2, we have 4. And you can probably see already that we're going to get the same steady state, because this here is still going to evaluate to 1, just like it did here, meaning that we're going to end up with the same solution. So this will just equal 2 plus 1 times 2 equals 4. And now we have a steady state. So these are the same. Steady state. Steady response time. Whatever. Therefore, the response time of task 2 equals 4, and its period was 10. So, and this is less than 10, therefore schedulable. So far, so good. everything we've looked at has been schedulable. Let's move down to task 3. Generally, this is where things start to get sort of a bit crappy, because as we also saw here, with a sort of a system that's running on the sort of the edge of its abilities, like at 0.93, things generally start to fall apart when you get to the last task on the system. So we have an execution time of 8 and a period of 30. This means that R3 equals 8. This is the first iteration. So in the second iteration, we have 8 plus the ceiling of 8 over, and now here we have a larger set. So firstly, we'll start with task 1. So this means we have 8 over 5 multiplied by 2 plus, was it 8? I should open this up on another computer. Task 2, 8 over 10 multiplied by 30. Was it 30? 10. 2, my bad, 2. So this is the execution. This is E1, was it? No, E2. And this is, was it P2? This is E1, P1. So if we do this, look at what's going to give us. We'll give us 8 plus, this here is going to be like 1.4. And so this is going to give us then the ceiling of 2. So we're going to have 2 times 2 plus the ceiling here of 0.8 will give us 1 times 2. So this is going to give us 2 plus 4 plus 2, right? So 8 plus 6 will give us 14. And so now we can move to the next iteration. So R3, 2, 8, 8 over 5. Oh, sorry, not 8, 14 goes in here now. 2 plus 14 over 10, 2. This gives us, what does this equal? Now we're no longer getting 2, we'll be getting 3. So we're going to have 8 plus 3 times 2 plus, and this here is going to give us 2 now instead of 1, 2 times 2. So this is going to give us 8 plus 6 plus 4. So we're going to get 18. 3, 3, 8 plus 18 over 5 plus 18 over 10 by 2. So what are we going to get now? This is still going to evaluate to 3. So that hasn't changed. And this is still going to evaluate to 2. So this also hasn't changed. So we're now going to get a steady state response. So we 3 times 2 plus 2 times 2. And this is also going to give us 18. So we now know that the response time of task 3 equals 18. What was its period? Its period was 30, right? And so this is less, wait, or is it 18? 6? Yeah. Oh, wait, no, this is wrong. This is wrong. I'm not done yet. This has changed. This is a 4. And so this is going to become 20. But if I can already see now that R3, 4 will give us the same, because the common denominator of 5 and 10 doesn't change given 20. So we have 20 over 5, 20 over 10, and this also gives us 20. So therefore, response time of task 3 is 20, and this is less than 30, therefore schedulable. Now, all tasks are schedulable. Therefore, entire system is set schedulable. Okay. So I think if that's everyone's sort of understood that, I hope that's quite simple. there's not really too much more that I want to go through in terms of scheduling. I think for the basics that I talked about in the lecture, these sort of cover it. My colleague Niels, I believe, is doing more advanced scheduling with you, and he'll probably go into more detail. But sort of the basics when it comes to like rate monotonic scheduling and just basic preemptive and non-preemptive, this should cover the basis of the theory. And as I said, with the real-time operating systems, for at least for this course, it's very much just theoretical knowledge that, for instance, you would use in like using scheduling. Okay, so you learn what a context switch is, and then you sort of understand how we can run multiple tasks on a system, for instance. So if any of my Zoom listeners have questions, I'm happy to answer them now. Otherwise, I'm done with what I wanted to go through because I also have some Christmas celebrations to get to now. Okay. So what does a period mean here? I'm not sure if you understood what it means already, but essentially when we're talking about the period here, the period of a task is how often it wants to be executed. So it's similar to a deadline, meaning that like if we look at this here, we have a period of 6, which means that every 6 ticks, the task gets made ready to run again. So your system wants to run this task every 6 ticks. And so that's what the period is. If we think about how tasks have their states, they can either be running, blocked, suspended. Essentially, every 6 ticks, the task gets put into the ready state so that the scheduler will now take it into consideration when deciding which task to put onto the CPU. Okay. So there's no more questions. I'm going to end this here, guys. I'm going to wish you all a Merry Christmas and a Happy Holidays. If you have any, is the period of the task, normally it's deadline. Not always. So you can have tasks that have a deadline and a period that are different. But for what we're dealing with, we're just dealing with the period and the deadline being the same thing. Because if you think about it, you want to run the task every 6 ticks. If it's not finished by the 6th tick, you've sort of, it hasn't fulfilled its purpose, right? But yeah, I would say in a lot of ways it normally is, right? At least for this course, you can think of it that way. Okay, guys, then I will, if you have any questions, especially with this, you guys can feel free to reach out to me. Maybe not over the next week, but once we're all back at uni and stuff, I'll be happy to respond to emails. So thanks, guys.